Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guest today is Matthijs Rijlaarsdam, co-founder and CEO of QuantWare. We discuss how his company is enabling the scaling of quantum processors through its VIO technology, a 3D chip architecture that addresses key bottlenecks in scaling qubits. Matthijs explains the three major challenges: fan-out, integration of components, and yield, and how VIO solves these to facilitate quantum chips with millions of qubits. He also shares insights into QuantWare's business model, which spans fully packaged chips, foundry services, and packaging services, drawing parallels to the semiconductor industry. Last, we explore the impact of heat, signal routing, and error correction, the strategic importance of marketing and storytelling in quantum industry, and much more. We hope you enjoy this episode. Hello, Matthijs, and thank you for joining me today.
Thanks so much for having me.
So who are you and what do you do?
So my name is Matthijs Rijlaarsdam. I'm co-founder, CEO of QuantWare. And we are a company that makes scaling technologies, a technology called VIO, for quantum processors. So basically we create 3D chip architectures to make quantum processors really large, much larger than you see today.
Could I buy a quantum processor from you, or do I come to you with a processor and you somehow make connect some of them together?
Actually, the answer is both. So we make this VIO, which we haven't been very public about, but we, let's say about, 70, 80% of the people at our company, which is by now a team of about 50 people, growing to 100 next year, they work on VIO. And with the way we bring VIO to market is in three product verticals. One is fully packaged chips. So indeed, you can go to our website and order a quantum processor. The second is foundry services. So it's, if you're a customer and you have a great design for a chip, you can come to us and we'll fabricate it. And because we have VIO, we can fabricate chips much larger than you otherwise would be able to get. And the third option, indeed, is like you say, it's basically packaging services. So a customer that is able to make quantum chips comes to us, and we package it in VIO, and therefore, again, they can make much larger chips than they otherwise would be able to.
How much larger is much larger?
Well, without revealing our non-public roadmap, and today we can do devices like the latest platform we have out is called VIO 176. So that's on the order of 176 signal lines. So depending on your architecture, about 100 to 200 qubits. But what VIO really gives our customers is a very the fastest path to go to 1 million qubits in a processor. And so without going in specifics when we think that will happen, that's a lot sooner than the other roadmaps in the field. And why we think that is important is that if you cannot make very large quantum processors, you need to resort to networking smaller nodes, smaller processors together. And that will work, and networking will be an important part of utility scale systems. But networking also has, transduction has high losses. The network itself has low fidelities. And so we think that it will be important to have these nodes as large as possible. And so that is what we focus on.
If I think about other superconducting qubit manufacturers, they indeed talk about networking. What is preventing them from building a chip with, say, 5,000 qubits on a single chip? What do you think is the limiting factor there?
So if you think about scaling superconducting chips, there are three main bottlenecks, and you named 5,000. There are some, let's say, intermediate solutions that you can probably go to about 5,000. I mean, you've seen, let's say, IBM's roadmap where they do go to that number, but depending on the architecture that they choose. But those three bottlenecks, they are one, fan outs. at the qubit chip level. And so what that means is in two-dimensional chips, you need to route the signal to the edges of the chip in order to create a little, what's called a wire bond, so a little connection to the printed circuit board and then to the outside world. And that doesn't scale for a variety of reasons. I mean, just practically, the signals traveling on the chip are analog. You want a lot of distance between them. If they're too close together, you get crosstalk. I mean, that's one, but also just very fundamentally, from a geometric perspective, if you think about it, the edges of a chip are one-dimensional. The area of a chip is two-dimensional, and that means that as you increase the number of qubits, you will run out of space at the edges to route your lines. And the problem actually is a little bit worse than that because you'll get crossovers over these lines, et cetera, et cetera. And so even at let's say our 25 qubit chip Contralto that you can buy on our website, about 80% of the chip space is used to route lines, not for the qubits. So that's the first problem. And so this means in order to solve this, you need to come in from the top. And it's also you can visualize this because the fan out gets worse than outside of the chip with really large printed circuit boards. And so you see these pictures of people holding 200 qubit quantum processors, and they really need to put their hands quite far apart. You can imagine going to 1 million qubits. You'll need printed circuit boards the size of soccer stadiums. Like it's not going to work. The second problem is integration of upset components. And so the integrated circuit has been a invention of in classical compute of 60 years ago, probably even longer. But in quantum computing, in superconducting quantum computing, all these, if this golden chandelier is completely full with golden little separate boxes, and those boxes contain signal conditioning components like filters and amplifiers. And those are separate superconducting chips in separate little metal boxes, and they look pretty small. But if you do the calculation, even at today's small sizes, couple grams per amplifier, if you go to 1 million qubits, you need to put hundreds or even thousands of kilos of equipment. Sorry, hundreds of thousands of kilos of equipment in your fridge. And so also that will simply not scale. And so you need to integrate that into your GPU. And that's the second thing that VIO does. So it's a fully silicon-based architecture. And so we have a lot of real estate there to integrate all of those components because, it's all made from the same materials. And then the third thing that that you need to solve is yields. And also this is just, pretty simple. Like eventually fabrication processes should be stable enough that you can make, 1 million qubits with high probability, but that scales exponentially bad, right? So if you have 99% probability that your qubit will work, which sounds pretty good, but that means if you make a chip of 100 qubits, the probability that all those qubits will work is 0. And so because it's 99% to the power n, where n is the number of qubits. So this scales exponentially bad. And so one of the ways to break that is to make a large chip out of many smaller chiplets. And so you need to solve all three of these problems. And there are many intermediate solutions that, maybe go to 1,000 qubits-ish. And you see some players on their roadmaps, like putting many chips together in one dimension, because then you can kind of get around the fan out, or you push it out a little bit further. But and you also see these players with, metal, what we call basically these blocks of aluminum where you put your chip in. All of that is either hard to produce or still very bulky, or you can't integrate those components. And so if you want to go to 1 million qubits, this is really something you need to solve.
And how does your technology solve these three problems?
Well, without revealing our secret sauce, and
not, we're friends here.
Yeah. No one's listening. we'll reveal more on this in the coming year or so. But summarizing a little bit, we create what's basically a 3D chip architecture. So we have a clever way of putting together many silicon chips, and because it's silicon based, so we put together many silicon chips. Those bring in the signal from the top towards the qubit plane. So it's 3-dimensional signal routing. We can integrate the components in this 3D chip architecture. Because it's silicon based, it's just the same type of stuff that the qubit plane is made of. And it takes in chiplets. And so the combination of those three things means that it's a very scalable platform, if you will.
How about heat? Is that a problem?
So, in general, the heat is a challenge if you want to scale. And that's because of two types of heat loads, basically in a fridge. One is active heat load, so it's the heat generated by the components themselves. That is fairly minimal. If we do those projections, that will not be a challenge to scale to 1 million qubits. And the second one is passive heat load, and that means that is the heat that is basically conducted by all the elements that, say if you have a signal carrying line, cable going from the coldest bit of the fridge where the QPU is to room temperature. Well, that's as isolated as you can make it, but it will conduct some heat. And that is actually one of the main problems. And so there are a number of clever things we are doing there that alleviate that problem far enough that you can at least get 1 million qubits in. And at that moment, again, because it's silicon based, you can integrate things like on-chip control. And also there, without going into specifics, there are a couple of steps there. One is creating an interface that is much smaller, and that's where also the signal carrying lines simply have a lot smaller footprint and therefore conduct less heat. That already pushes it out to very large qubit counts. And then there are a few other clever tricks that we do that make this more of a matter of let's say it's more of an infrastructure problem rather than a science problem at that moment.
When you spoke about fan out, you mentioned the 1D versus 2D problem, that the edge is essentially one-dimensional and the surface before your architecture is two-dimensional. And let's even assume you solved that. But if every qubit needs 2 or 3 control wires, then 1 million qubits still need 2 or 3 million control wires. How do you solve that problem? The number of wires. I mean, if I look at a Intel CPU, it may have thousands of wires or thousands of leads and billions of transistors. So how do you get around the million wires problem?
Yeah, so that's kind of exactly what our architecture solves, right? In fact, we the architecture that we will most likely use, what we're designing around, it has more than 4 million lines. So there's definitely if you route in 3 dimensions with all the signal shielding that we do there, that's exactly the problem that we solve, because indeed you need to solve that. And then of course, you have these things like the SFQ that generates using classical superconducting electronics, generates the analog signals from digital signals coming in. Well, then you can multiplex. So that's, in the very long term, also makes the heat load in the fridge less, basically, if you will. And we have a long-standing partnership with Seek on innovation like that. There are various other things there. So that's one step further away than where VIO is positioned. What VIO solves is exactly the problem that you sketch, getting millions of lines to the qubit plane.
What is the status of the technology? I mean, you mentioned that one could buy a chip off your website. Um, who is your customer, or who are your customers, or what are the types of customers you're looking to work with?
Right. So it's important to, in terms of customers, to make a distinction of the majority of our customers today. They are customers of our fully packaged processors. And so those are system integrators, most of them commercial. We currently have customers in about 19 countries. So we're fairly, international. I think by terms of volume, we are one of the largest providers of quantum chips. Um, and but VIO, we've just started to roll out to a few selective customers, and that's the VIO 176 platform that I told you about. Um, because VIO is modular, expect that number to go up very rapidly in the coming years. And then we also expect that so now the emphasis, we talked about these three product verticals, right? Fully packaged chips, foundry services, and packaging services. The emphasis right now is on fully packaged chips. We expect that to shift to foundry services and packaging services because the key differentiator of QuantWare is VIO. And VIO will, if you use VIO, you'll be able to make much larger chips than the competition. And so we expect that there will be that there will be a shift towards those other two verticals. Yeah, and then of course, in foundry services, it means fabless chip designers, of which there are a lot more than you might think. Especially because there are quite a few players that do primarily develop design IP, and they have a little fab team to do R&D chips of like a couple qubits. But that's something else than having the ability to build chips of hundreds, thousands, and then hundreds of thousands of qubits. That segment, that's where those players will come in. And the third one, those are obviously players that need to have the capability to make chiplets of relevant sizes. So that's fairly sizable players.
And thus, if the company is very successful, and I try to make the classical computing analogy, you'll be the TSMC of quantum, or the Intel of quantum, making CPUs, and disregarding the current problems at Intel.
Right. Yeah. Well, that's a very good question. And also referring to the problems at Intel. When we started, we didn't have those other two verticals. We only had the fully packaged chips. And so we also refer to ourselves as the Intel of quantum. We don't do that anymore for obvious reasons. But indeed, it's like you say, these three verticals, they basically correspond to three different business models, right? The fully packaged chips is Intel, the middle one is TSMC, and the right one is something like, I don't know, Besi or something. One of those large semiconductor packaging companies that most people have never heard of, but are actually really large companies. And um, to some extent, if you like pulled it out 20 years from now, you're gonna need to make a choice, because if you, in a way, if you're doing, say, foundry servers or fully packaged chips, you're competing with your own customers to some extent. How that will pan out, like in the current state of the market, I think it's fair to have all three. And how that will pan out, yeah, it depends on how the market will pan out. And to give that, we've seen that in the past as well, right? When we started, we were the first to introduce commercially available quantum processors. Soprano was the world's first quantum processor that was commercially available. That has changed a lot of business models in the industry. So there are now pure play system integrators, parties that build and sell quantum computers that don't make their own chips. We've seen a massive acceleration in the field thanks to that. We've provided the chip for the first quantum computer in, I think, now 5 different nations, including fairly large ones. So that has really changed. And then in response, you could see players like, I don't know, Rigetti all of a sudden brought out the Novera product. So you could see also other players reacting to our value proposition. And, the Rigetti sells compute, right? They want to sell quantum as a service. and now they're also selling chips. So they are, in that sense, similarly positioned that in the long run, you're going to need to make a decision because, otherwise you're competing with yourself in that case. And so, or with your own customers. And so, but, in this phase of the market, I think it's fair to have all three, but at some point, going back all the way back to your question, right now we're all of the above.
I was listening to the Google Willow presentation a few weeks ago, and they described some clever ways in how they're overcoming, two photon states and crosstalk and cosmic rays and resets and many other phenomena. Do you have to solve the same issues, or does the architecture provide, maybe a complete different set of problems?
Yeah, some of those, yes. Some of those, no. And some of those, we don't know yet. I don't know. Let's say 2-qubit gate protocols. That's much more on the design IP side, or error-protected qubits, something like that. That's not something QuantWare will do soon, right? We need to have design IP to ship our fully packaged products. So we do have a sizable design team, but we use generic transponders for that. So that's not really where our focus is. And again, I mean, that makes sense because, let's say, for the foundry services, we'd want to service error-protected qubits designers, right? So those are not the type of problems we're likely to solve. Things that are more related to the shielding, the packaging, the routing of signals through silicon vias, chip stacking, that kind of stuff. That's really where our bread and butter is. And of course, fabrication. So if we're talking about coherence improvements, making very good TSVs, doing clever things with housings, that's really where our bread and butter is. And so in that sense, you referred to the Widow announcement. I think that's a really good example of why VIO is so important. It's a fantastic improvement, and it's a big milestone, and it puts the ball back in the court of the other platforms, right? Because finally a big step is made again. But at the same time, it's a doubling of qubits in 5 years. That's not fast enough. That's not gonna, then we're never getting there. We need to get that way up, and that's hard if you don't have a good architecture.
Let me try to maybe stretch the classical compute analogy maybe a little bit too far. You'll tell me. But once upon a time, CPUs had the math coprocessors to the side, and then over time they became integrated, and then even CPUs have sort of some kind of GPUs integrated in them, so it's not just a set of chips. So when we speak about error correction has a lot of classical components for the decoding and analysis and so on. Do you expect to integrate classical components or classical compute on your chip, or is error correction completely external? I mean, one could make a claim, maybe not true, that 1,000,000 qubits is a fantastic achievement, but it's useless if you don't have error correction attached to it.
So I fully agree. We need error correction, especially superconducting qubits are great because they're super fast, right? And at scale, speed matters, because if you need to do a lot of operations, if you have a lot of circuit depth and your operations are 1,000 to 1,000,000 times slower, then yes, you could calculate it, but it would take 10 years, and therefore still wouldn't be economical. So speed matters at scale. But, as we all know, they're noisy. So you will need to do error correction. It better be fast, because otherwise there goes your speed advantage. So the latency of that hardware and all of that is super important. So there, we're fully aligned. Then to your question of, will there be basically classical compute on your chip? Well, not on the chip. It will be what will be there in VIO itself at some point is SFQ, which is I guess, classical compute, superconducting, but classical compute. But that will be also at various stages of the fridge. The reason for that is that classical compute generates heat, which we don't want or like. But if you talk about 1,000,000 qubits in a QPU, you might have seen the paper. I think it was a collaboration between Rigetti and Riverlane, where they show real-time error correction for superconducting qubits using external hardware. There are a few of innovations like that make a system of that scale possible with what is actually right now very mature technology. I mean, it's a very large size, right? And if you start designing a system like it, you run into silly things like the ports on that equipment are too large, so that at that scale, the physical size of those ports will be too large, right? So you'll run into issues like that, but you don't need to integrate that hardware on chip in order to go to 1,000,000 qubits. You'd want to do that beyond, but to get to 1,000,000 qubits, you don't need to do it.
How about connectivity? I know that in some other superconducting manufacturers, they went from each qubit is connected to 2 or 3 and maybe soon 6 and something like that. Does that matter in your architecture? Do you have an improvement along those dimensions?
Well, that's really more of a design choice rather than a platform choice. So again, what VIO provides is a way to get the signal in from the top, and then there's a way to route that signal in various ways. And so the default easiest, or let's say simplest way, is to indeed have a 2D grid to do surface codes. But if you want to make, I don't know, long distance connections, then that's totally possible. That's really more on the design side. We just provide, let's say, the platform for people to design novel error correcting code that might use long distance copying.
You mentioned VIO. You mentioned VIO multiple times. Is that an acronym for something?
No, it's not. It's just VIO.
Very good. As we get closer to the end of our conversation, I'm curious, what have you learned about the market in the last 12 months that, say, you didn't know before that?
Well, I mean, I definitely learned something about the power of marketing, given what the stock market did after the Willow announcement, which contained not a lot of new information compared to the archive publication that was out months before. So I think that's definitely still both an opportunity and also a risk, that this industry is still very hype sensitive. Also learned a lot around, we talked a lot about VIO, whereas our website tells very little about VIO. And so for me, as a CEO, it's a clear indication that our storytelling needs to improve a lot. And I think for the rest, I think for a lot of quantum companies, apart from the 10x push at the end of the year in the stock market, for a lot of quantum companies, at least the ones that I've spoken to, not been the easiest year. I think a lot of people feel they put in a lot of work and sold in less than they wanted to, but then at the end of the year, a lot of very interesting and cool stuff happened again. So in that sense, I think it was a very interesting year. I am super optimistic for the next 2 years ahead. I think a lot more will happen than people expect. And I'm excited for what's to come.
In last hypothetical, if you could have dinner with one of the quantum or semiconductor greats, dead or alive, who would that be?
I think two names come to mind. One, which is an obvious answer, but for his strategic vision and how far he thought ahead of what happens now, Jensen Huang. Right, I think that's such a good example of a company that was able to position itself in a adjacent market before getting the big prize. So that would be, that's super inspiring. And the other, who's a personal hero of mine, would be Scott Arison, who I admire a lot, and who I think is one of the greatest thinkers in where the applications of quantum computers will be.
Matthijs, thank you so much for joining me today.
Likewise. Thank you.